Hello everyone. Today I'll be explaining to you guys this two very important algorithms in topic graph, and two of them are Bellman and Floyd Warshall. We'll first start with the Bellman algorithm. Given a weighted, directed, and connected graph of V vertices and E edges, find the shortest distance of all the vertices from the source vertex S. If the vertices can't be reached from S, then mark the distance as 10 raised to the power 8. Note, if the graph contains a negative cycle, then return an array consisting of only minus 1. So what we are set to do is to find from a given source vertex to all the other vertex the shortest path. So the only difference between Bellman and Floyd partial is an all pair algorithm. That is from in this algorithm we tend to find the shortest path of every node to every other node. But in this we find the shortest path from one particular given node, that is the source node, to all the other nodes. Now why was it introduced at the first place? It was introduced due to a specific case that Dijkstra algorithm cannot handle. And the case was when the graph has negative weights. For instance, from 0 to 1, the weight of the edge is 9. Whereas from here is 1 to 2, the weight of the edge is minus 1. This case can be very well handled by this Dijkstra algorithm. But this case, when the weight is negative as well, cannot be handled by Dijkstra as well. So in order to overcome this issue with the Dijkstra algorithm, the Bellman algorithm was introduced. Okay, so how will we code this? In Bellman algorithm, we want to anything just relax the vortexes. And how long do we relax? We relax it for n minus 1 times. Okay. So we'll keep on relaxing it, keep on relaxing it. What does relaxation means? Relaxation simply means that if from 0 to let's say we go, and from 2 to let's say we go to 1, there are two possible paths. I mean, no, from 1 let's say we go to 2. Yeah, there are 0. There are two possible paths. But from 1 you directly go to 0, the possible path is 3, and the weight of the graph is edge is 3. So it will cost you 3 rupees, let's say. But if you tend to go from 1 to 2 and then from 2 to 1, you will be reaching at effective price of 0, because this will cost you minus 1 and this will cost you 1. So, which path will you choose? Will definitely choose 1 to 2 and from 2 to 0 instead of choosing from 1 to directly going to 0. So, this is what this is what is supposed to be found. Which is the shortest path from any one node? Let's say here the case is 2. So, from 2, if we have to go to every other node, which is the shortest path possible. That is the way to do it. And let's say if we cannot reach to a particular node, then we'll have to, not include that case. We'll be initializing that with 10 to the power 8. And if the graph contains a negative cycle, we'll have to simply return minus 1. How will we find the graph contains a negative cycle? It is only possible uh, in case of the graph containing a negative cycle. No matter how long we keep relaxing the vertices, it will still not be relaxed. So let's say we have to relax this for n minus 1 time, right? Then if we do that for n time, even then the graph won't be relaxed, right? What does relaxation mean? Relaxation means nothing but distance of u. Let's say we are going from u to v. Okay, what does relaxation mean? We check the distance u plus weight of the graph is less than distance v, right? If from the source, what is distance u? From the source, we go to u, and the cost of that is given by distance of u, and the cost of going from the source node to vertex v is given by distance of v. So if the cost of going to u and then going from u to v is less than the cost of going directly to v, then we'll relax it. We'll relax it how? We'll just initialize. I mean, we'll just change the value of distance of v to distance of u plus v. This is the process of relaxation. This is what we are doing now. We are relaxing the edge, relaxing from a very high strain to something which is less than that. So that is how we relax. We keep on relaxing that until n minus 1 times. And even if, like, let's say, if the graph has no negative cycle, after n minus 1 cycles, after n minus 1 relaxations, the graph will never fall under this case because all of the edges right would have relaxed. But in case the graph is negative cycle, this case will still prevail. In that case, we'll have to return an array that is consisting of only minus 1. So now let me begin doing this. Begin with b vertices. So we'll run a loop from 0 to b minus 1 because we have to run for b minus 1 times I plus plus. We'll have to extract the edge matrix that is given to us. The edge array given to us is having the source in it, the u vertex from u to the vertex v that we're going to, and the weight. So this will give us from every edge to every other edge that are connected to each other and the weight of it. Say 0 to 1 is connected by the edge weight of 5. So we'll have 0, 1, 5. 1 to 2 we are connected with what? With edge weight of minus 1. So 1 to 2 and edge weight of minus 1. So this is how it goes. So how will we extract this? We'll extract the first element of this will be giving us the source vertex, I mean the u vertex, and 1 will be giving us the other vertex from u to where we are going to, and the edge weight between them. That's what is given by the third element. So this is how we'll extract. We'll traverse this of auto id and edges, and u will be given by the first element, right? So id of u, and v will be given by the second element's id of 1, and the weight between them will be given by id of 2. You'll understand this very easily. Like we have extracted the things that we want to extract in order to relax, and how will we react? How will we relax? We'll simply uh, run this condition. If distance of u plus weight is less than distance of v, well, relax distance of v to distance of u plus wait. Now we'll have to first initialize, right, the distance vector. So we'll initialize that of the size b to 1 e raised to power 8, and raised to power 8 is what we'll initialize this to. And if this is the case, because initially no edges are accessible from any other edge, right? So I mean, in the distance vector case, we put it that way so that we can get the minimum possible distance every time. So this is what we'll do, and we'll do keep on doing this for how many times? For b minus 1 times. This is what we are doing. After this, had this been relaxed, had there been no negative cycles in the graph, there would be no more wanting to relax it again. So we'll try doing this again. If distance of u plus weight is less than distance of v. Now see, by this point in time, we would have relaxed all the edges for sure had there been no negative cycle. But in case there exists a negative cycle, what? In case there exists a negative cycle, what we'll do is we'll return what? And when will this graph contain negative cycle? When this condition still prevails. When this condition still prevails, even after running this for b minus 1 times, that is, even after running this for n minus 1 times, it is prevailing, right? So even after relaxing all the edges, it is not getting relaxed. Means this graph has a negative cycle. In that case, we'll simply return minus 1. I guess you would be knowing already what a negative cycle is. And yeah, this is what we have to do. And last, we'll return the what? Return the distance. Yeah. Q was not declared. Oh yeah. Hmm. We have to also initialize the source. From the source, the distance is 0, right? This is what we initialize. U was not declared in the scope. Oh yeah, we'll have to take the source, right? Let's see. This should be fine now. Yeah, submit this and see. Yep, it is working perfectly fine. What we did is simply we relaxed this for n minus 1 times, and had there been no negative cycle, this condition wouldn't have prevailed, and we would have directly returned distance vector, but they said us to return minus 1 in case the graph has a negative cycle. So we'll just, this is just for checking. If checking if the graph has a negative cycle, ignore the spelling mistake of checking. There is a typo, and yeah. So only this is just to check if the graph has a negative cycle, this condition will prevail and will not return distance, instead will return minus 1. So that is what we have to do, and I guess you would have understood. After the code, it is even much simpler, right? What you have to do. So you have to extract the elements from u to v. You are going into x between them is weight, and you just keep on relaxing. Keep on. You don't have to do this. This is done by loop already, and you just recheck it once and then return the distance. Now we'll go to solving this Floyd Warshall algorithm. As said earlier, the difference between this and that is this is an all pair shortest path algorithm in which you know from every node to every other node you know the shortest distance. And this is slightly let's say not complicated, but a long sort of approach which I cannot right now explain properly because I don't have a pen marker or board as of now. So, but let me tell you what this basically means. Okay, so if you have to go from let's say node U to node V, there are two possibilities, right? Either you directly go from node U to node V, or you go from node U to node W, and then from W you go to V. This is the only two possibility you will have. You will either directly go, or you will go to through some points. Right? This W is not a single node. This can be any other path in between. Let's say W might have X in it, and this can further have A in it, and then from you'll cross this and you'll go right. So I'm just telling this for a perspective point of view. That you can go through any other path, or you can go directly right. So this is the only, we'll take the minimum of this condition. That is the only thing which we are doing in the Floyd Warshall algorithm. For that, we keep a matrix from 0 to 0. The only possibility is, I mean, from 0 to 0, you go to 0, right? From that particular node to that particular node, from the same node to same node, it will be 0, right? From 1 to 1 also, it is 0. But from 0 to 1, if you go, you'll have to pay 25 rupees. And from 1 to 0, you cannot go, hence it is minus 1. But had there been a case when you had from 1 to 2, you could have gone, and from 2 to 0, we had from 1 to 2, you go, and from 2 to uh, 0 you go, right? And that is costing you 20 rupees. You would have chosen that, right? You would have gone from 1 to 2, 10 rupees, and 2 to 0, 10 rupees. That would have costed you 20 rupees. But from here in this case, from 1 to 0, if you go directly, it's costing you 25. This is much more than what 20 is. Yeah, this example might have that situation. From 0 to 2, you are going with a price of 43. But you are going from 0 to 1 as 1 rupee, and from 1 to 2, you go 6 rupees. So what is it costing you? From 0 to 1, you go 1 rupee. From 1 to 2, you go 6 rupees. The net cost you're incurring is 7 rupees. Had you been going from 0 to 2, you would have paid 43 rupees, which is much more than what 7 rupees is. So this is how we keep this metrics, and we keep updating it every time, like after every traversal, so that this metrics at the very end will have the shortest path. So that is what the question wants you to do. We do not have to create any other data structure. You just have to update it in place, right? You just have to do it in place. So I hope you would have understood this. Let me now go to coding it. We first initialize the matrix I is less than I plus plus, or is equal to 0, is less than. I mean, the matrix is already given to us. We're just changing it in a case that when it is not reachable, right? So when it is not reachable, it's instead of putting it minus 1, you'll put it a very large value so that it will never be considered by the algorithm. So if matrix of I and j is equal to minus 1, we'll just change this to a very larger value so that it does not get counted at any point in time in the future. And if I is equal to 0, what do you do? Just initialize that to 0. Why? Why so? Because from that particular index to that particular index, the shortest path will always be what? The same, right? From 0 to 0, you're not doing anything, right? You're already on 0 and you have to go to 0. So the cost will be 0. So that is how we initialize this. Now is when we use this ideology. What? That is from 0 to V you are going. You can either go, the case 1 is, you directly go from U to V. And the case 2 is you go to a medium. That is a medium. That is through something you're doing. And let's say that medium is K. Medium, say K. So in that case, what will your path be? To K and B. And K can consist of many nodes. So this is what the idea is. You just have to code this, and I is equal to 0, I is less than. No, K is what you're doing, right? So K is 0, K is less than K plus plus. Oh, you didn't do anything. You had a 2D matrix, right? That is taken care by this I and J thing. And the K is only for checking if there is any other path or not. Like through that path you're going, you can go or not. So matrix of I and J is equal to minimum of what? Minimum from I to J you're going, right? So it can be either matrix of I direct path, or it can be what? It can be matrix of I to K, right? I to K, and from K to J. This is only two conditions you can check, right? It can either be direct from I to J, or it can be from J to K, from I to K, and then from K to J. That is what I mentioned before. And this will keep on updating that, and I guess we'll be good to go. Yes. This is the only thing we have to do. I mean, Floyd Warshall and this Bellman Ford is very small in understanding. Okay, fine. You just have to declare just a hyped version of algorithms. Since it is from the graph and it is at the very end. Oh, yeah. Okay, so the question said us to change. I guess this said us to change the graph is represented. Yeah, you have to. The question didn't tell, but we have considered this ourselves, right? If the matrix of ij is -1, we change that to a very large value so that it is not encountered later on any time. So we'll have to get back to that point, right? In times equal to have to get back to -1. If matrix of ij is equal to 1 e to the power 9 is what we had initialized this to. We'll change this back to matrix of ij is equal to -1, that the node is not reachable. So yeah, by the time they compile, the time complexity of this code is in cube, because this is the three uh, for loops that we are using one after the other, and one inside the other. And what do you say, the space complexity is order of 1, because we are just modifying this given array itself. Why is it taking so long to compile? Mm, 0 of n square plus of n cube plus of n square. System is also lagging a bit. We'll wait for some time. Yeah. Unable to process a request now. Why so? Let me directly submit it then. It's not compiling for some reason. Right. Uh, yep, submitted it directly. And yeah, it is working. Yeah, it did work. So that is all for this video. I hope you have understood the approach. The approach is very simple. I know that there might be a bit of a problem in understanding what Freud Warshall is, but I would suggest you to watch other videos, or maybe go through some articles given in the TFG itself, because I don't have this pen, the on-screen pen or something. Uh, Pen tablet or something in order to explain this very well. But I hope you would have understood the approach, what this is, right? There can be two possibilities, and we are checking for the best of both. That is what we are doing in the time complexity of this being O of n cube, and the space is 1, and yeah, that is what for this video. Until next time, thank you.